at 7.
This Young Winners Special is presented through grants by USF&G Insurance, Providence Savings Bank, and the members of the Maryland Center for Public Broadcasting.
Welcome to the 6th Annual Physics Olympics. Today we're here at the University of Maryland. Hello, I'm Willie B. O'Brien. The 1983 Physics Olympics is part of a series of programs produced by the Maryland Center for Public Broadcasting and dedicated to young winners who exemplify a positive winning attitude in a wide variety of activities ranging from science to sports to art. These Olympics today are sponsored by the University of Maryland Physics Department. Today we have over 30 high schools from around the state of Maryland competing in 5 mandatory physics events and 2 of 3 optional contests. Judges for the Olympics are drawn from each high school represented here today, the faculty of the University of Maryland, and physics department graduate students. The term physics, as you may know, comes from the Greek word meaning nature. It deals with the how and the why things work in a vast spectrum of scientific fields, covering mechanics, heat, light, electricity, even things like magnetism, sound, atomic energy, and solid-state properties. At times today, the events covered will look like a field trip to Mr. Wizard's basement or a sketch from Rube Goldberg's drawing board. Speaking of Mr. Wizard, we have Dr. John Lehman here, University of Maryland Physics Department. Welcome, Dr. Lehman.
Welcome, Willie.
We're glad that you have us down here today. We have a lot to look forward to, and you're going to be with us for all the events, right?
Absolutely.
To explain to those of us that may not be as professed as you are in the subjects exactly what is going on.
Yes.
Okay, quite a day planned. This is like Christmas for you, so we're looking forward to it. All right?
Yes.
Okay, we'll be back with Dr. John Lehman. Right now, let's go to one of our first mandatory competitions, the egg drop. Now, the object here is to carefully construct a protective package for an egg so that when the egg is dropped from a specified height into a metal plate, the egg remains unbroken. That's the key here. Now, the judges will also be computing the length of time for the fall, with the most points going to the shortest time of the actual descent.
Madison? Oh, she's already got it. Yeah.
All right, warm up. Looks good. Looks good. Bro! Not that. Is that the type of reaction you want? Tell him I had no time. Oh, yes. Why would you put this in candy? Yeah. Yeah, we're good. Yeah. Yeah. Oh, yeah. 3 minutes. No time, it broke. That was Madison. Madison, no time.
Now, Dr. Lehman, you would think there's only so many ways to package an egg, right? But over the years...
Until you come to a competition like this, that's what you think. One day spent here and you find there are more varieties than there are students in the schools.
What are we overall looking for? What is the bottom line factor in getting an egg from the 4th floor to the metal plate unbroken? What's the long-term objective?
They can treat it essentially as a ballistic device, simply dropping straight down. Or in some instances, they will add fins and some sort of stabilization to somehow control the flight. There is no perfect scheme, and there's no guarantee that any judge can look at the design of the student and say, yes, that will survive, right, the other one will not.
Right, see. And what's the, how is this applicable to a long-term physics work?
Well, in the long run, the basic objective is to have them solve a problem, to not offer preconceived designs and preconceived procedures, but to simply say to the student, we'll give you the height, we will drop it onto the hardest surface. At that point, you have to solve the remaining problems.
So in other words, what would appear to be a very, very simple type of contest with all the different variations you have here becomes downright technically difficult.
Absolutely, and the simpleness is apparent to those watching the egg that's finally dropped in its carton.
But not to those doing it, right?
Absolutely not, and not to those who have spent literally probably many drops trying to perfect the packaging procedure. All of that, of course, goes on in the schools and is not visible to the people watching the egg drop here at Maryland.
176 if it's any good. Okay, Flint Hill, let's do it. No hurry, just take your time. This is national TV, don't be nervous. Yeah, sure. Just mind the course. Hey, well done, well done. Ask her again. Tell them what our secret weapon was. Answer it, sorry.
Yes!
5.
Huh?
Well, it will be, apparently. Roosevelt? Yeah, Roosevelt.
Very good, Johnny. Thank you.
No time on Roosevelt, no time.
Well, that one, that was different phone. That phone was...
We have Wakefield.
Wakefield, that's it.
Okay, let's go. Let's see if it works anyway. When it hit, it was about 400. Yeah, we'll get away. Well, it made it. Come on. The time was about 350. Yes, it's a shame you can't get it on the series. Well, you got another run, Wakefield. I'll put it in about 350. Next time I'll be awake, and I'll stop it with this device instead. It's a great idea. Package it up and let's run it again. Neat idea. Okay, 73. Right. Yes! Fantastic.
Take your time, Ron.
Wall church number 2 was no time. It held, man. No time. All right. Suitland 1 is up right now. 169. Unreal time. Unreal time.
Nice design, too. Yeah.
Just quick and dirty, right?
Don't drop it now.
Don't drop it now. Yeah, Ron. Take time. Boy, I'll need the threads back here if you break it.
Still have a minute and a half.
Plenty of time, Ron. Take it slow.
Hurry up, Ron.
CDA got to get.
Yes, by 4 ATUs.
Take it easy.
Here we go.
Is it good? Number 2.
Don't see any yellow yet.
You don't have 1 minute.
No, don't hurry, don't hurry.
Don't hurry. No one's ever failed to get it out yet.
You really hit, yeah, 2 minutes is up. All right.
Would you look at that? He's really wrapped.
It looks
It looks good.
Ron, did you make it?
Bring it over here.
Good. 169. 169.
There you go.
go. That's the egg that made it to number one. Where's the poster at, Ruth? Get the poster. The poster, Sophie. Number one egg. Okay. Wait a minute.
Okay, now we come to one of our optional events. Now remember, each team must compete in at least 2 of the 3 optional events. Now, this will never be mistaken for the Indianapolis 500. We have right now, just what the name implies, a slow bicycle race. And the object is to travel over a prescribed course in the slowest, and we mean slowest amount of time. That's a feat most of us out-of-shape cyclists feel we could do with ease, but this is really very difficult because the challenge is that the competitors may not touch the ground or floor or stop their movement while they travel. So let's see how it goes. Now, Dr. Lehman, a rose by any other name is still the same, and this obviously applies to bicycles in this case, right?
Well, except that bicycles, as you can see from the pictures, mean many things to many students.
And obviously, if it means laying down and pedaling with your hands, it's still a bicycle.
Absolutely. We've defined the rules to be 2 wheels coplanar with one another, a rate of progress that has to be forward, the fact that they can't touch the edge of the course, and beyond that, what becomes a bicycle is up to the team.
Now, have we seen a design like this before? This looks pretty original.
There was one last year, and once a design has appeared that has proven successful, it will reappear even in other schools.
Now, when you have a case like this where one design obviously could win year after year after year, what do you do?
Then you begin modifying the rules and at least creating categories of entries so that all entries have some chance when they arrive at the competition for being first place.
So next year we'll look forward possibly to more of a typical bicycle, right?
The kids have met our challenge, and now it's time to change.
Well, that's what you're looking for overall, and congratulations.
Thank you.
By the end of this, we're going to know each other real well.
Well, there's one man here I never want to get behind on the expressway, Terry Fu from Wooten High School. You must be pretty proud of yourself. Now, you're traveling how far in the course here in the slow bicycle race?
It was a 20-meter track.
20-meter track, and it just took you how long?
71 minutes, a little over.
71 minutes, a little over, give or take a few, to travel just right down the hallway here. Now, your bicycle design, you're pedaling it by hand, right?
Mm-hmm. I just have my hands on the front wheel and just flip it over back and forth.
Now, Wooten does very well every year in the Physics Olympics. You must have a pretty good chance in the bicycle competition. How do you feel thus far?
Well, I mean, I just want to contribute to our team. Just hopefully we'll just do a good job by the end of the day.
Was there anything you were thinking about as you raced along the course, or were you just, you probably could have finished the 5th chapter or Gone with the Wind while you laid there, right?
Well, it was extremely boring, so I just decided not to think about anything. Just get the thing over with.
Okay, how do you practice this? How do you get in shape? Eat a lot of donuts, pastries? What's the story here?
My physics teacher would let me practice in 6th period for my school. I just go down the halls when no one's around.
Well, it's rough, the end of a long day at school, to have to go lay down on a bicycle and stroll around for 77 minutes over 20 meters, right?
Yeah, but I get to miss a class, so.
Well, let me tell you, if I was going to be at Wooten High School, I think I'd be sure to sign up for the slow bicycle race. Listen, Terry, you're doing very well so far. Give our best to all your friends at Wooten, and thank you very much, okay?
Okay, thank you. Yeah.
What's the time? About hour 25. It's worth it. Yes, it is.
It's worth it. It's worth it.
Everybody but him thinks that.
I'm just going to tell you that thing, you know. You can put in your college application that I rode a slow bike for 2 hours.
Yeah, I rode a slow bike.
I'm very
Slow bike. What the heck is a slow bike?
You don't know what slow is. Let's see all of the guys up at West Point do this speed.
Yeah.
This kid's got patience.
You can have PA and it's cadet. Probably.
You want to try it. You got about 6 or 7 moving speed. 5 meters to go to speed down. Slow, but keep it moving. Just think like you're rolling in Miss Cook's face. Yeah. He can laugh, he can talk. He won't laugh.
He won't laugh. Are you kidding? He won't laugh.
No,
You got 15
You got the moving speed.
Got to that second white line. You got a long way to go yet. Let's go. Sun's going down.
Keep it slow, Steve.
Sing to yourself, Steve.
Originally, my brother invented that design last year, okay? And he brought this design last year and won it here, and also we went to Indiana and won it. And no one else even thought of the design. And as you can see this year, everybody's brought the same one. So far, Wooten, I guess, is the best, which is 77 minutes for one run, one half run. Right now, we are at 1 hour, 35, 40 minutes. So we are doing significantly better. No, I don't know about that bike down there. He seems to be doing okay.
I'm not sure what it my watch is 2 minutes or 2 hours.
Oh, it's not that bad right now, but because I get to lie down, but it's pretty tiring. I've been on for over 2 hours, and I don't know, my legs kind of feel dead.
Well, if you're an engineer or a troll, you'll really get a kick out of our third mandatory event. It's bridge building, and using only balsa wood and glue, each team must construct a bridge within certain specified dimensions. Now, the bridges will then be test loaded, and although the load is far shy from, let's say, the Bay Bridge on Memorial Day weekend, it's still a formidable task. And the bridge supporting the greatest load is going to be today's winner. So let's see how the action is going. Dr. Lehman, what we have here, as I heard you say earlier, is more of a bridge-destroying competition as opposed to bridge building. Now, the bottom line here is not so much to support weight, but that we have a bridge supporting weight with all that a bridge implies, right?
Yes, we found early on in the competition, if the only thing that we measured was the weight supported, some of the devices brought in did not resemble bridges. As a consequence, we had to add additional requirements, such as the two ends of the device have to support 10 kilograms of mass. A small car must run across the surface, because if there's no surface, that allows extra balsa wood in the support members, which gives them a small advantage. But if there's no surface, of course, then it's not a bridge.
Now, when you say a small car, we actually have small Matchbox cars designed in proportion to run across the bridge, right?
Yes, and it's interesting that the bridge will support the small Matchbox car to define it as a bridge and turn around and support literally hundreds of pounds. And this, of course, on a balsa wood bridge that weighs only or less than 110 grams.
Now, it seems to me in layman's terms, there are certain types of bridges, and it's within a limited category that you could define all bridges, a suspension bridge, et cetera, et cetera. But what we see here is the most unique bridges I've ever seen, and we're varying off the course from what we come to know and accept as your standard bridge. So obviously, in the world of bridge building, there's still a lot of ground to be covered, right?
I think so. Some of these really ought to receive prizes for their physical appearance, even if they don't turn out to sustain the largest load. And in the future, I think we're going to have to generate such a category.
Okay, we'll start with half. Okay, we'll try the one. Kind of recheck your clearance. We'll take this off and we'll add another 2 kilograms. Count 3. Count 1, 2, 3. Okay. All right, let's take off the weight and put another. Put another brick on. Okay. Real key thing.
You can take 1.5 off and put a 2 on, something like that.
22 right there.
Well, you want to go with another break?
Watch your knees, man.
Okay, watch your knees. You waving my knees, one of my favorite positions.
23.
All right, let me get it. 24, 25, 26. All right.
Jeff, we're going to get him.
Okay.
Thanks, Mike.
Hold on, Mike, your side is going.
Not balanced? No, this bar's out too far. You pull one off because I just took one off. I'll stick the bar a little bit further back in.
This way.
Yeah, just try to slide the bar in between them. I'll hold this.
Hold on.
Scoot it over.
Okay, that's good, that's good. Mike, it's flexible. You're You guys on this next one. Get ready to put this stuff back.
Remember, hang your stop the go. Okay, we're here with Andrew Hogan. Your job today is kind of the overseer of the bridge building or bridge destroying contest, right?
More bridge destroying right now than bridge building. The construction of the bridge is extremely important. What is at least as important as the design of the bridge is whether or not all the joints are exactly mated to each other, and the care of construction is an awful lot of the strength of the bridge.
That's a good point, because we've seen bridges which look almost identical, but one falls far before the other. So like you said before, the way that they're glued together, the joints and so forth, really do, would you say that's the bottom line? And how, in addition to the obvious design, that the construction itself, how it is done, has a large effect?
Definitely, definitely. Another one that is a factor is how the bridge is loaded. That's why we let the students load their own bridges rather than doing it for them.
You guys do it right. You can put one so it's sticking off.
And what kind of weight are we dealing with here? How much are we up to so far in some of the various bridges you've seen?
The largest one that we're loading right now, and it still hasn't broken, is around 160 pounds, and winning bridges are usually in the neighborhood of around 200 pounds.
All right, Mike, let's see if we can lay mine. Like you said, ladies flat, all right? I think the one below three. The black way. Never mind. All right. You get yours? Yeah. All right. One, two, three. Leaning. It is. It's bound. All right. I tell you what. Wait for me, right? No. You get it in there? I see it. All right. I got it. Move it over to the left. Towards me. Towards me. Okay. Got contact? Yeah. Down slowly, Mike. Okay, now. Hold on. I think it's going to rock. Slide yours towards you, Mike. That way. Away from me. Away from Will, yeah. Come on, a little more. Okay, hold on. Up. Mike, can you take off 2 bricks? I got him. 1, 2, 3. Take this one off my hands. Let's go back and lay these flat. I got this one. I'm sorry, Will. No, I'm not complaining about that. It's just because I don't want these things to start flying. All right, I'm going to take this one out. Eventually, you run into the same job again. 1. All right. We're going to lay these flat and flat. Lay them flat. Got your fingers out here? Got it. Line it up on the bricks below it. Contact. Hold it. Keep it steady. Contact. Nope. Don't lean. Here. Slide it. Slide it. Well. Lean it. All right. Flip the rope. Oh, no. How are we going to do this? Kevin, wait. Let's see what you're doing. What do you want to do next time? If those aren't going to fit, take them off. Mike, first, get your hands down and hold the bottom. Don't let the bottom rotate at all. All right? Don't put the hands on. All right, 1, 2, 3. Get it out there, Mike. Is that better, Will? Oh, better every time. I think that's good enough. You want to? We're going to go. Want to make sure not level. Check it yourself. You want to move? Does it rock when you do it? Is it stable, Will? It feels all right. Oh, what are you doing? Trying to see this? All right, go ahead. It's starting to bend? Yeah. All right. It's going to give. Move out, people. It is bending. Yeah. All right, it's going to go. Hey, yeah. I think I heard it right there. That's 4 now. That's bending. Let's say this one's going in and that one's going out. Right. And once it starts going, it's going to give.
What we have here is called the solar furnace. Now, in this contest, each team tries to harness the power of the sun. And given certain design specifications, what they're trying to do is build a solar furnace. The team building the furnace that is able to change the temperature of a fixed amount of water by the greatest number of degrees and a certain amount of time is the winner. So let's proceed onward and get up to our necks in hot water. Even when the sun is not out, the heat may still be on. Right, Dr. Lehman?
Absolutely, and that's one of the critical features of this particular event. The students have first-hand evidence that even though it's cloudy, there's energy coming through the clouds, and that can play a major role in, for instance, heating their homes.
Now, we're looking to change the water to a certain temperature in a certain amount of time, and we understand that this is a University of Maryland physics event original, right?
Absolutely. This event began here at the university and is now in the pool of events that is kept track of by the American Association of Physics Teachers. The primary specification is the size of the opening through which the sunlight can come in. All of the rest of the design is left up to the students, and all of them will have some success even on this cloudy day.
Now, I don't see evidence of things that, in layman's terms, you would imagine would absorb a lot of heat. Tin foil, for example. Are there materials which these students are aware of which work even better than that?
Most of the students are using the tin foil to reflect the light onto a surface that will generally be painted black. That's the surface that will generally absorb the heat and cause the change in the temperature of the water. The aluminum foil is simply to gather the light and bring it into a smaller area where they've confined the water.
Do you find that you have better success where the water is enclosed, where the heat is able to absorb and stay better? I see a wide variation here. That's why I asked. Some are very wide open while others are very narrow.
I suspect those that are enclosed will be a little more successful today because there's a breeze. And with the breeze, there's always heat energy loss that you don't have if you have a piece of glass or some other surface over the water itself.
This is Alec from Bowie High School down in Bowie, Maryland. Now, we have something completely different here from some of the other solar furnaces we've seen. You have the water obviously is within the cylinder, I presume?
Mm-hmm. The 2 liters fit almost perfectly in the cylinder. There's just about 7 milliliters of air space.
Okay, now what kind of material is this reflective material?
Sheet metal aluminum.
Okay, in other words, basically, the thing about solar energy that amazes me is that it is ultimately so simple. And from what I see here, you're catching the sun, reflecting it, within, you know, your aluminum shield here. Now, what about conducting it to the cylinder itself? I mean, the heat will just radiate from the cylinder?
Well, with the parabola, it when the sunlight comes perpendicular to the parabola, it'll reflect the sunlight in a way that it hits the copper tube at 2 inches, a line 2 inches above the parabola, and it radiates a lot of heat. And it's a copper tube, and that'll conduct the heat through the whole tube, and it'll get to the water.
Now, we got kind of a windy day today. Would this kind of furnace be affected by that?
Yes. If it was a real sunny day, it would heat up a lot faster.
Well, only time will tell. We wish you a lot of luck. Say hi to everybody at Bowie High School for us. Thanks a lot, Alec.
Thank you.
We're here with David from James Madison High School in Vienna. On a sunny day like this, you would be by far more advantageous to have this kind of solar setup, but unfortunately, you're at the mercy of the elements, right?
Yes, very much so.
Now, you have here what looks like a piece of glass, but it's not really. This is tempered or designed specifically to catch heat, right?
It's basically designed to concentrate the light. It basically works like a large magnifying glass. To concentrate the light down to one focal point, it gets to be about an inch in diameter.
So the bottom line with a device like this is not necessarily the greenhouse effect or the infrared rays, but just actual light and heat itself. So you were telling me earlier that what had you done with a piece of bark in like 15 seconds?
The other day, I had a wet piece of bark out on a sunny day about 3 o'clock in the afternoon. I incinerated that in about 15 seconds, so if I had light, it would really be doing great.
So on a sunny day, you'd have it all going for you right here. We wish you a lot of luck anyway, okay,
Yeah.
David, from James Madison High School.
Thank you.
And now in the solar furnace competition, I'm here with Mark from North Hagerstown High School. North Hagerstown has a real winning tradition as far as the solar furnace competition goes, winning twice out of the last 4 years, but your predecessors are gone, you have new teachers, and we're looking at something which is completely different from what's been used in the past. Now, basically, what are you trying to do here, Mark?
Well, the rays from the sun, the ultraviolet rays, they come down and they go through the glass, okay, and they hit this black surface area, which absorbs the heat.
Right.
Okay. Now, it's kind of like a greenhouse effect where it won't come back out. The infrared rays, which are produced inside the thing,
They don't bounce back out.
Yeah, they won't come back out because of the glass. And that's basically what it is, and it heats up the water, too.
Now, do you have the water confined in there, or is it just leveled out across the whole area?
It's inside the container in there. It's a black container.
Okay, it's hard to see the container. Is there any reason why, now we know the black absorbs the heat, but I also noticed that the frame is white. Is there any reason for that?
Judges want it that way. That's the rules. That's the only way.
Okay, well, it looks nice. Well, may you continue your winning tradition at North Hagerstown High School. Good luck here, and I don't normally wish people a lot of hot water, but in your case, we wish you well, okay?
Okay.
Thank you, Mark. Here we have Ina from Gaithersburg High School. Ina tells me this is her first year taking physics, and you've been so enthused by what you've been exposed to, you're going to major in it next year, right?
I hope to.
Okay. Now, what we have here, you're obviously trying to catch the rays of the sun. You've got the two plates angled, and we see there's no conductor, though, going from the plates to the water itself. Is it better just for the heat to try to radiate up?
Yes, actually, those two spherical dishes act as mirrors, and they focus the light from the sun onto the bottom of the pan. Thus, no conductors are really needed. The sunlight actually is reflected onto it.
Now, is there any way, though, you could have, like, put a piece of glass over the pot there to have a greenhouse effect in addition to just the heat radiating itself?
That's very possible. I've seen a number of exhibits that do have that effect, but we felt that this, with the actual, just like on the top of a stove, you don't actually keep something
True.
covered.
It's evened out more. Is the wind affecting this kind of design at all?
Yes, it would affect a little as the wind blows across. It would pick up some of the heat that's already into the water, so that is a slight problem.
Okay, Ina from Gaithersburg, we wish you a lot of luck, and good luck in your physics career also.
Okay, thank you.
It's funny how we're all trying for the same end result here, but there's really many variations on the same theme. From Wakefield High School, this is Dana. Dana, we see here, instead of the greenhouse effect like we've seen previous, you have more or less just kind of a dish. You're, trying to pinpoint the heat and the silver part in the center, and then what?
Yeah, well, that's really what we're trying to do, use the focus point. It's a paraboloid surface, and it's really sort of paradoxical because the reason I built this, we didn't build it just specifically for the Physics Olympics, being it cost a lot for the materials and make it, was for a science fair, a local science fair, a high school in the area one, and in that one we proved that this was less efficient than the passive solar heating for the same amount of area.
Really?
Yeah, but since we had already had it, and then suddenly the Physics Olympics came up, we decided to use it for
Now we see there's really no direct conductor, though, from your focus point below to the kettle of water above. I mean, the heat itself is enough to radiate to do it on its own?
We decided on our surface, the best thing for, a mirror to reflect the rays to the point. And we figured perhaps mirrors or small mirrors or something like that, but just the cost and the amount of work needed, decided that tin foil would probably be the best.
Dana, do you have any designs on solar engineering? You seem to know what you're talking about here.
Well, I find it pretty interesting, somewhat, but it doesn't have much applications in this area, maybe down in Arizona.
Well, hopefully in the future, and the sun will always be there. Dana, thank you very much, and good luck to everybody at Wakefield, okay?
Let me have your attention over there. With the water, after you get your temperature done, and it's recorded there, come over to us to get your volume checked.
Good heavens. Wooten, 102.1.
Okay.
Oh, well.
St. Albans, 93.4. Hey, what's in there?
It's just in caulk. It smells awful.
You sure there's no chemical reactions going on in there?
No.
96.0 for which?
Not bad.
Which one? Wheaton. Any others?
This is the event that allows the students to have no preparation ahead of time. We select 3 pieces of apparatus from our lecture demonstration collection, move them into a room. Students are then asked to come in as teams, watch the behavior of the apparatus, and then provide us with explanations for the behavior based on physics.
Come on in. All right. Obviously what we have here is a beaker of water sitting on a balance. Okay, it's nicely balanced. Now the question, there are 2 parts to this. The first question is, if you stick your finger in this, what's going to happen? Now you stick it in part of the way so you don't touch the bottom of the beaker. So if you just put it in the water, what's going to happen? Is the apparent weight of the beaker going to be, is the whole thing going to be heavier or lighter? Or stay the same, obviously, main choice. So we have those are the main choices. You have 3
I suspect that many students indicated it would not because the finger was not allowed to touch the bottom of the beaker, when in fact the putting of the finger in the beaker causes water to be displaced. That displacement of water causes an unbalanced force, and the beaker and system become heavier.
Okay. Answer.
It's the main thing.
All right. Volunteer. Someone put their finger in it and let's see what it does. Don't touch the bottom, put it in. Okay. So what did it do? Which means it got heavier. Okay. Now, spend another 2 or 3 minutes and discuss why did it get heavier? Okay.
Well, putting the water, the weight from the fingers and not the water pushing.
Okay, you can try that. Now you're welcome to do whatever you want to tonight.
No, it doesn't.
See, when you put your finger in, the column of water is going to rise. The pressure determined at the bottom is determined by the height of the water, and it doesn't matter this. It's just raising it. So the column is going to be higher, and it's going to be exerting a greater pressure on the bottom. The height is going up.
Anybody else have anything to add about that?
The formula they have.
Like dropping a little rock inside.
Pressure equals
Drop
what?
the rock,
Height times-
as long as the bottom rises, weight of the beaker.
Okay, well, okay, good. Let's go on to the next one.
The second device was a light pipe. This device was chosen by the professor in charge of this event, and it's something that has been withdrawn from the research collection. It's a very new kind of transparent material that can gather light, absorb the light, re-emit it, and then the light travels to the end of the rod as though it were a light pipe or something similar to fiber optics, which is now a common term in the telephone industry, where information is sent via light beams as opposed to electrical signals over wires.
You can't because of the angle it would have to hit it at.
Can we
The
touch
crucial angle.
Well, yeah, you can touch it.
As it gets farther from the source, it fades a little bit.
But why doesn't it go for a clear one?
Because it depends. It's the what's inside it that does it. A clear one has a different crucial angle when the light enters.
Okay, what is your explanation?
It's something along the lines of Hooke's law. The light gets in there, and because of the angle, it can't get out because of the crucial angle. Because of that is the fluid that's inside or whatever, the material. So it gets reflected around. It can only get out the ends because of the
the angle it's at the surface. That's the only place it can escape.
Okay.
It's getting, well, once light enters, it's going to get reflected from all the different sides. It's basically a squarish, internally reflected, and the only path of escape is the two sides. So it just keeps reflected until it gets out.
Okay.
The third event involved nothing more than a ping pong ball in a funnel, and when air is blown through the funnel, it would seem to blow the ping pong ball out of the funnel, when in fact air pressure differences hold the ping pong ball in even when the funnel's upside down. If you wanted the technical term, it's Bernoulli's principle. The general term that we would expect from the students is recognition of variations in air pressure.
I think we can do that right now.
No, wait a minute. Okay. So what I want you to explain is why. And you're welcome to check the ping pong ball out.
It's just like that pool with the...
You can go, if you know the answer right away, you can just go ahead and tell us.
Something along the line of Bernoulli's principle. When you're blowing into that tube, the air is rushing over the top edge of the ball really quickly, and the pressure is lower. And the normal atmospheric pressure on the ball is greater, and it's pushing up and holding it in there.
That's very good. You got it exactly right. That's what's going on here.
Well, Casper Weinberger and the Defense Department might be especially interested in this Physics Olympics event. It's called the Coat Hook Cannon. Now, basically, the object of the contest is to sculpt a wire coat hanger into a prescribed shape so it can effectively launch a projectile. Now, there are two rounds, if you'll pardon the pun, to this event. The first is called the Fort Ticonderoga Lob. Now, in this round, the projectile must be launched from an elevated and horizontal position toward a randomly placed target. Now, the second round of this artillery fire power demonstration is called the Tartagliarian Triumph. In this round, the competitors control the angle of the launch, but the target and the cannon are both on the same level. And just to make things a little more difficult, a randomly placed object is placed between the cannon and the target. Now, each team gets 3 launches per round. The judges compute the scoring based on the accuracy of the firing. So now let's go down below and hopefully get blown away. In this round of the Coat Hook Cannon competition, Dr. John Lehman is here with me. Now, what basically are we looking at here? What's the overall purpose of taking the projectile from point A to point B?
The idea is to have students have to reach a target with the projectile, but the energy to reach the target is gained by pulling the coat hook cannon back to a prescribed height, so that when the projectile comes back to the lower position, it is in effect launched into the air and must in effect try to hit the center of the target. But it's primarily a conservation of energy situation.
So overall, let's say for future careers or how this could be applied as far as physics goes, what basically are we trying to do here?
This would be a broad introduction to mechanics, the whole idea of conservation of energy, of the idea of a pendulum and its behavior, of a projectile. Projectiles are a very common problem in introductory physics, so this is simply a continuation of that. And this is an area where students frequently do a great deal of problem work, but don't always have experiments to go on with it.
Is this the kind of thing that the students were able to practice ahead of time for, or do they realize the setup here, or is it something that they're put on the spot with?
They have the full description of the apparatus and have built the equivalent apparatus back in their own school.
So as far as the Tartagliarian Triumph goes, we're really making life difficult for some of these students here because above and beyond what we've already seen, we have a randomly placed object in the middle, right, between the cannon and the target.
Absolutely. We've moved the launcher down to floor level. We've placed a barrier in between the launcher and the landing point so that the projectile has to travel up over the barrier, which means that students need to do a few more calculations.
So basically, the bottom line, what we're trying to learn here is just the laws of physics, more or less, and this is a real abstract way to see where action comes into evidence, right?
This is a good basic application of the laws of mechanics, something that would be covered in the work of all high school physics, whereas occasionally they don't get into electricity and magnetism. All of them will have covered the mechanics.
Now, the students, were they aware ahead of time of the exact ways and designs in which this is going to work, or was this something thrown upon them as they arrived here?
Now, they have full details for this particular event, and they have certainly built the equivalent apparatus back in their own schools and done a great deal of practice. And some evidence of that is when they bring protractors and other angle measuring devices and are obviously applying rules that they have learned by practice back in their own schools when they come into this competition.
I like, all right. No, don't look like it. Yeah. So you should shoot like it. Okay now? All right, guys? It bounced off sideways. It had to hit. I heard it. No, it didn't hit. No, it didn't hit. No. Which way was it on? To the line. Yeah, okay, I got it. All right. That was a hit. That's a great shot. Like Braddock, thank you very much.
Okay, we're about to watch Falls Church High School. They've had their practice shots now.
One more. One more. One more. I haven't got time to give you one more. Okay?
And the object is to land right on the bullseye there. The pad placed at the 40 mark. Still off to the side some. Interesting to note, though, how a lot of the students are using direct line of sight and just anticipation of action-reaction as opposed to calculating it out. Some of these students, as we have noticed here, instinctively have that ability. We'll find out if those in Falls Church do. Almost on the side, but not quite close enough. Just slight fractions off. A minor change in the angle here, combining their resources. And a bullseye for Falls Church.
Falls Church, thank you very much. Now you need to...
Now, to the casual observer, this optional physics event may appear to be more closely related to a concert than a scientific experiment. But believe you me, nobody's going to be scalping tickets for this musical happening. The judges will be evaluating the musical talents of our young scientists. Now, the object of the contest is to have each team create an ensemble that will play tunes on homemade instruments. The instruments must be designed and built from materials not commercially available for producing music. The instruments should be designed to produce a variety of sounds so that a musical piece can actually be performed. The judges will be awarding points for creativity and workmanship, the range of notes, and the quality of sound and performance. And as Lawrence Welk would say, a one and a two and a let there be music. From Eleanor Roosevelt High School, Becky, that was a fine warm-up there. How do you feel, huh?
Fine.
How long before the actual concert tour starts?
Well, we already did ours. We did ours this morning.
Oh, okay. Well, we got a lot of good vibes here. You're making this out of what? Just pipes or what?
Yeah, pipes. Part of it's from a swing set. The other part's from someone's house.
Never a dull moment at Becky's house or at Roosevelt High School. We wish you a lot of luck in this part of the contest, okay?
Thank you.
Thanks for being with us. Well, you know, everything is relative. One man's candy is another man's poison. One man's chock full of nuts can is another man's musical masterpiece. We have Brock here from, where are you from?
Bowie.
Bowie High School. And you guys put together quite an ensemble here. Now, we have, this is what, a tar can?
Was the bottom of the tar can, yeah.
All right, creative genius abounded. Now, you want to tell us what else we have down the line here?
Oh, this is these are the array of coffee cans in different tones, all precision tuned by us, of course.
I can tell. It's got that masterful,
Yeah.
pounded-in look to it there, the dents.
And we were supposed to have some beakers, but our physics teacher forgot to bring them, so we had to acquire some new instruments for ourselves that were very recently acquired, as a matter of fact.
Somehow these gentlemen have improvised. Well, for the first time since you put this group together, you'll hear the word encore. So how about a little bit more from Bowie High School, okay?
All right, no problem.
Willie B. here in the Young Winners, and Let There Be Music. We're here with a music competition, and we're making music with everything except things you make music with. Now, from Lake Braddock Secondary School in Virginia, you are?
I'm Robert Schaefer.
Okay, Robert, are you thirsty or what?
Well, no, there's a point to all this. These are I just set this up like a xylophone. What I've got is a series of glasses here of different sizes and with varying levels of water in them. And the more water you put in, you get a lower pitch, and so you just vary the water levels.
You even have them, the notes marked on the side of the glass.
Well,
now,
that's what it is.
the guy here next to you, what do we have, a Tupperware party or what?
Well, this is just kind of an improvised drum set, and he's just got Tupperware containers and coffee cans, and on one he's put a bunch of pennies in it, so it sounds kind of like a snare drum.
Ah, yes. That's on the far end there. Okay, now, with all of this, what do you perform, Babalu or what?
Well, no, we all kind of threw this together at the last minute, and so we worked something out in the practice room before we were scheduled.
Why don't you throw something together for us and give us a sample of your wares, so to speak, okay? Lake Braddock, here we go.
Yeah, of course.
More or less or more. Thank you very much. Good job there.
Now, in case you haven't been here in years past, we don't encourage you to make it a habit of coming to this 5 and 6 years running, because that's a long time to remain a junior or a senior in any school. We are feeding the scores into an Apple microcomputer. We will turn on the video monitor, and when the ranking occurs for a given event, you will see it at the same time I've seen it or anyone else has seen it, with the exception of 1 or 2 shady judges in the back that had to enter it. On the other hand, when we finally do the summary for the event, and we say, yes, we would like to rank score, even the judges in the back room will have not seen that yet. And at that moment, it will be displayed, and we will all know simultaneously which team, if any team, won the event. Let us display the results for our coat hook cannon. Tension builds each time. It should say, explain the apparatus. Is that? Hello. Overall ranking for the whole competition.
Well, for the first time in the 6-year history of the University of Maryland Physics Olympics, we have a repeat winner from Rockville. It's Wootton High School. Congratulations, Umar.
Thanks a lot. It was really a team effort. Everybody gave their full, and it pulled through in that sense. Because everybody just came through. Some events we thought we'd place a little higher. Some events we didn't think we'd place quite as high as we did. But in the end, it seemed like we came out first.
Obviously so. You're holding it in your hand. With the evidence speaks for itself. Now, although you won last year, you only have one person on your entire team that was here last year, right? So pretty much you've really done it on your own instead of resting on your laurels.
Yes, that, and we had some aid from last year. We had some
Mr. Bascom told us some of the ideas that other people used last year, and we improved upon them.
How about it, you guys? Anybody spurring toward a career in physics now as a result of what has happened here today? We wish you all more or less. You think so, seriously? Let's hope so. Umar, we wish you a lot of luck. Who's heading the physics department over at your school?
Mr. Bascom.
Okay. Well, our best to him also and everybody at Wooten High School. And congratulations for a job well done. Well, I think you'll agree that today we've certainly proven that science isn't a dull exercise performed only with chalkboards and notebooks. Science can be fascinating, fun, and filled with the joy of making discoveries about the world and ourselves. This is Willie B. O'Brien on behalf of the University of Maryland Physics Department, the Maryland Center for Public Broadcasting, and myself, thanking you for joining us and watching today's edition of The Young Winners.
Don't forget, next Saturday at 2, the first finals in the MPSSAA Girls Softball Championships. But right now, it's a look into how man has viewed the heavens throughout history. Next on Cosmos, coming up on Maryland Public TV.
This Young Winners Special was presented through grants by USF&G Insurance, Providence Savings Bank, and the members of the Maryland Center for Public Broadcasting.
Take yourself to the ball game when the best girls softball teams in Maryland high schools match up for the Fast Pitch Softball Championship. Be there with Willie B. O'Brien, Jim West, and Ted Patterson to cheer for your team. Watch the Young Winners in Divisions C and B on Saturday, June 4th, beginning at 2, and in Divisions A and AA on Sunday, June 5th, beginning at 3.
The battle with Mud Creek. That's likely what the history book will call it.
Have ordered the Battle of Champions for December 3rd. Be sure to watch the fight confirmation test broadcast nightly. Please watch tomorrow at 7. This is the only way you can confirm your order.